Hello everyone, welcome to today's lecture. So today we're going to be talking about nonlinear problems. Actually we've been talking about nonlinear problems for quite a while. Pretty much every parameter dependence that we've had in our model reduction pipeline has somehow been a nonlinear parameter or a nonlinear dependence, right? If we subdivide our domain in multiple sections and we have different stiffnesses in each section, then the whole problem behaves non-linearly with respect to the different components. So that's not the type of nonlinearity that we're talking about. The type of nonlinearity that we're talking about is with respect to the trial function, the solution itself, right? So a nonlinear PDE in the sense that in the partial differential equation we have maybe hyperbolic tangent acting on the solution, or we have a solution times the solution itself, right? The square dependence. And that's the type of problems that we want to also be able to address in the model reduction framework. So why is this important? Well, I suppose that if I talk with civil engineers and I talk about nonlinear problems, then we should be quite familiar with two types of these in the context of solid mechanics. So let's focus on those and use those as sort of examples as we're moving forward. So, what nonlinearities are we familiar with in solid mechanics? So the equation that we're always kind of dealing with is one of deformation under load, right? And the one that we're familiar with from a linear perspective is the one from linear elasticity. And that one looked like this. So linear elasticity. Yeah, so in our bilinear form is an integral over our domain. And we have this linear strain on V, our test function. And the strain is now a second order tensor. That's double contracted with a stiffness, which is a fourth order tensor, which is double contracted with the linear strain acting on the solution. That's integrated over that domain. Right? So, and our linear strain in this case is defined if we take the linear strain of any vector valued function. And that is defined in this case as the symmetric gradient, which is half of the gradient of V plus the gradient of V transpose. And there's different ways of deriving this equation, right? You can talk about a weighted residual approach, where we're going from the strong form, multiplying by a test function, doing integration over a domain, doing integration by parts. Or we have also derived in this class these equations from an energy potential and taking a minimization. And due to the kind of the symmetric nature of a whole bunch of these terms, we can shuffle around things. So I think different depending on the way that we derive this. Actually, this term might originally have been on the right, but due to the symmetries of our stiffness matrices, we can shift those around. So those are actually things we'll see later on again. Small thing that I wanted to point out is that this part of the equation is then actually the stress corresponding to our displacement field U. Now this is linear elasticity, right? If we look at our two dependent variables, being V and U, a test function and a trial function, then they are linear with respect to both of those functions. Yeah? If I double V, then well, the gradient is a linear operator, so that's also doubles. And this integral is a linear operation, so that also doubles. And also if I add another function to V, it also splits, so it satisfies all the linearity requirements. So what kind of nonlinearities are we then familiar with in this context? Well, the two things that always show up as examples are material nonlinearities and geometric nonlinearities. And let's talk about material nonlinearities first. So the only way that the material really shows up in these equations is through the stiffness tensor, right? So that's also where that nonlinearity is going to sit. So that would mean that the integral equation changes and I'll kind of separate this as best as possible, so I'm still going to make use of these linear strains. But now our stiffness tensor itself depends on our strain at that location, at some location. So when does something like this occur? Well, clearly if we're talking about an elastic response, then that's not relevant. But at some point, once the material gets past a certain stress level, it tends to deform plastically, maybe with a certain hardening. So there might be a kink in our graph, right? So this is our strain in some direction, this would be our stress. And so it allows an additional flexure, which means that the stiffness response of our system is no longer a linear function, but there's a dependency on our epsilon, our strain, right? So that's what this has to do with. Now, is that important? Well, yes, certainly. If we look at, for instance, an arbitrary bracket, we have a clamping and a certain load, then depending on whether or not we take into account this plastic behavior, which would probably occur around here, right? This would be the stress location. You might have very different configurations in the final deformation, but also certainly in the final stress state, right? So linearity is an assumption that tends to not be valid for these kind of peak stress locations, and by adding a plastic behavior, we are actually releasing part of those stresses. So it's very important for solid mechanics. Then the second type of nonlinearity is geometric nonlinearity. So geometric nonlinearity. And there's actually a whole bunch of different interpretations to geometric nonlinearity. Often we think of buckling as a nonlinear, geometrically nonlinear behavior, snap through. Another example is that if I were to have a string in space, so there's no gravity acting or there's no weight acting, putting it down, and I would apply a certain load vertical to that string. From a linear perspective, the only thing that is able to counter that load is the bending stiffness of our string. Well, a string doesn't really have any bending stiffness, so if you were to perform a linear analysis on that, using a finite element method, it would completely overprotect the deformation of the string. Whereas if you do a geometrically nonlinear analysis on the same example, then after it deforms a little bit, it recognizes that it actually also the tensile part of the problem becomes important. So again, due to the deformation, we get a different stiffness behavior, and that comes into play for geometric nonlinearities. Now I'll actually focus on a key example here, and that's the case of rotations, right? If we have a rotation of a member, rigid body rotation, then there should not be any strain due to that, and there should not be any stress due to that. And what we're going to have to do is we're going to have to change our definition of our strains over here, because these actually show non-zero values for rotations. And I'll show that in just a second. So what we're going to do is we're going to change our formulation to an integral. We're still going to use linear strains with respect to our test function. With respect to our test function, everything is always linear by nature of how we derive our equations. For this example, we're going to keep our stiffness also linear, right? I want to separate these into two examples, although in practice you might actually want to combine these two. And now the strain definition on our trial function is going to be different, so I'll use a capital E for that. So there's still going to be a second order tensor, still going to depend on our deformation, but in a slightly different way. Yeah, so the way that we could, for instance, define our strain, this is Cauchy-Green strain, if I'm not mistaken, is that we take the linear part of this, and we're going to add to this half of the gradient of the deformation transposed times the gradient of the deformation. Now this might look a little funny, unless you've done this a couple of times, it is actually quite confusing why we would have to change something like this, because it seems so obvious that you simply take the gradients of deformations and okay, that we symmetrize that, we also can intuitively understand. So what are we doing here? Well, I think that a very clear example is if you look at a deformation state that takes a block in a standard configuration, and the block has, I don't know, fibers in this direction, but that's mostly just to show its orientation, and we're going to rotate this guy by 90 degrees. So then we would get a configuration that looks like this. Now you can write the deformation for each point. You get a simple translation matrix or rotation matrix. Sorry. Then you can define our linear, so you can compute the linear strain for that. And the linear strain that you would get in this case would actually look like this. Right, so the strain tensor that you would obtain for a deformation like this, where we've simply rotated a block of material by 90 degrees, which is obviously a very extreme deformation, but it should definitely not introduce any strains or stresses. Then what the linear strain observes or tells you that's going on is a 100% compression in both x and y. Right? And that actually kind of makes sense, because if I look at a vector along this direction, well, this vector is now flipped completely upwards. So my length in x, from a linear perspective, has shrunk to 0, right? I have a 100% compression. And similarly, my length in y is also rotated onto the x-axis, which means that from a linear perspective, it has shrunk from a length of 1 to a length of 0. Nevertheless, we clearly see that that's not what we want our strain measure to show. We want our strain measure to show 0 strain. And if you then actually work this out and you also multiply through these gradients, then we find that this strain measure is actually going to give you a 0 everywhere. Yeah, so that's what we expect. So this is just a quick argument for why we're interested in this stuff. There's different kinds of strain measures, and that also kind of has to do with sort of the arbitrary nature of strain. It's really not like a fundamental quantity. It's really just some kinematic relation that we ourselves define because we need some sort of closure between our stresses and our deformation state. So we're actually pretty free in our choices. Clearly we have some properties in mind that we want. We want it to be localized, and hence we're talking about gradients as opposed to actual values of deformation. And we expect certain behavior, like we want 0 stresses if it's purely rotative. But other than that, we're relatively free, and that's kind of where these different strain definitions come from. Examples are that you could measure with respect to some reference configuration, right, which would naturally be a rest configuration, but it kind of doesn't have to be. And if you compare with a reference or a rest configuration, then you actually get this big E. But you could also compare it with respect to a final configuration, and it would just be as consistent. Or you could work in an iterative sense, that along your deformation path you increment your strains and compare every new deformation with respect to its current state. And then you actually get logarithmic strain, right? And it all kind of makes sense, so it kind of depends on what is the most convenient use. Now, and the nice thing about all these strain measures is that if you have very, very small deformations and very small rotations, then they all collapse into this standard linear strain expression, right? So that's the one that we're always familiar with using. Yeah, okay, so that's probably a rather long story about strains, but still something that I wanted to point out. I feel like there was something else I wanted to say. Maybe we'll pop back into my head. So we have two different types of nonlinear problems, and I've specified these now according to their bilinear forms. Right? We have a bilinear form here, we have a bilinear form here, and they kind of show different properties in terms of how we would treat this in the model order reduction framework, and that's why I'm highlighting these two. Yeah? So we'll get to that in a second, but first, before we do that, we kind of have to reiterate how we go about tackling problems like these. I'm not sure how familiar everybody is with of nonlinear finite element methods. So I'll give a bit of a rehearsal, but also because I don't want to bore anyone, I'll do this probably in a little bit different way than what you might be familiar with. I'll focus more on the functional side of things, right? So typically if we talk about finite elements, then at some point we're very used to think about matrices, stiffness matrices, and we kind of derive the whole thing from a matrix perspective. But I'll also try to also give the flavor of the functional perspective of everything in there, to give a bit of a balance, right? In these lectures I've addressed a number of times that there's very strong correlation between linear algebra, matrices, vectors, and functional analysis, bilinear forms, linear forms. So I'll try to highlight that also in this talk. So, how do we solve this again? So let's again talk a bit more general, right? These are two specific examples that we'll get back to in a second, but now I'm going to talk first about a general example of a nonlinear problem. So I have here A, which is no longer a bilinear form. This is actually this encodes a nonlinear partial differential equation, where we have a solution state phi, a test function v, and since we're still in a parametric sense, we still have this parameter dependence mu. And we're looking for the solution that phi satisfies this equality where our nonlinear left-hand side is equal to actually some linear form on v on the right-hand side. Yeah, so this L is still a linear form, but A might have nonlinearities. And normally this is actually the way that we look at solving a PDE, a linear PDE, right? We have left-hand side equals the right-hand side, and the left-hand side is a bilinear form, and the right-hand side is a linear form. But since the left-hand side is not a bilinear form anymore, we're going to have to do this differently altogether. What we're going to do instead is we're going to define a residual. And we're going to interpret this residual to be a linear form with respect to v, our test function, for a given solution phi, and in our case also a given parameter point, right? We still always have this parameter variability in there. So this is what we define to be the residual. And we can define this as the right-hand side L, again a linear form with respect to v, minus the left-hand side, which was some nonlinear dependence on phi, but still a linear dependence on v. Yeah, so I also said, even for our nonlinear equations, we always have a linear dependence on a test function. So this is really only a seemingly small change of notation. We'll actually see that this is somewhat important later on. But the objective now is no longer to solve for a function phi that satisfies this equation, but rather we're looking for phi such that the residual for that given phi is equal to 0 for all our choices of our test functions, yeah, which might be in our Sobolev space, H1. Now, so the residual is a linear form with respect to the test function. What was a linear form? Well, a linear form in everything that we've been talking about is some operation, some object that takes a function in our Sobolev space and gives us a number. Right? And this is a linear form that takes a test function and assumes that it has been given already a solution phi and a parameter point mu. So then it takes a test function and it gives a number. And once we find the solution phi such that the residual, that number that the residual gives back for any possible choice of test function is 0, well then we say that is the solution of our nonlinear partial differential equation. Now, okay, we've been saying this analogy between linear algebra and functional analysis kind of follows from that linear forms have a correlation with vectors and bilinear forms have correlations with matrices. And that is particularly strong once you start to discretize, right? So once we use a finite element discretization, then that becomes a one-to-one analogy. So let me also draw that analogy here. So I think I'll try to make this consistent in a second. Let me first write this out. So suppose that after we discretize, then our linear form will become a vector, which means that we now have a vector R that depends on, well, our solution phi, but again, sort of the components of this vector that describe phi, and our parameter point mu. And an operation of a linear form acting on a function, that was this notation of a transpose vector standing on a, or multiplied with a standing vector. Yeah, so again we have here the v components. And that is the same operation now. That has to be 0. And now for all choices of v, well, no longer in a sublow space, right? We've discretized, we made this into a vector notation. So now this guy is a vector in R n, where big N is the number of degrees of freedom in our finite element grid. Now, saying that a vector multiplication is equal to 0 for all possible vectors is saying the same thing as that our vector R mu is simply equal to the 0 vector. So that's kind of how we, in our finite element framework and our finite element write out, we somehow get a statement that is independent of the test functions. That's because of this step. So I think I will kind of, well, that doesn't look like anything. Maybe I will create sort of a, it's not any better, is it? Sort of. I think that once I print this, it's going to be fine. So I'll use green to denote sort of the analogy with linear forms and linear algebra. Okay. So the way that we solve nonlinear problems is that we're going to start. We start with some sort of an initial guess. Phi naught, phi 0. And this might be a solution that we have obtained from the same equations, but throwing out a bunch of the nonlinearities. If we think about the Navier-Stokes equations, then we typically find the initial guess from the Stokes equations. In a solid mechanics application, we typically tend to do these load increments, so then the first initial guess might actually simply be a static case, and after we've solved for one load increment, then the new initial guess for the next load increment would be the solution from that previous increment. Right, so we have some sort of initial guess. Now clearly, our initial guess is not going to satisfy our partial differential equation in this statement. That's not going to be satisfied. Yeah, so we have that the residual acting on our linearly acting on our test function v for this initial guess and our parameter point, that's not going to be equal to 0. At least not for every possible test function v. It might be 0 for some test functions v. It's certainly 0 for the trivial choice v is equal to 0. But it's not going to be 0 for all possible choices of test functions. That's our demand. That's what we're looking for. So we have an initial guess, and we want our solution statement to be equal to 0, but it's not. So how do we proceed? Well, it makes sense to iteratively proceed and iteratively add sort of an increment that moves us towards 0, right? That's a very natural way of thinking here. So let me also write the linear algebra analogy here. So our vector R, using this phi hat 0, is not equal to the 0 vector. Yeah? That's it. Again, the analogy. Can I still get rid of this? Yeah, then I'll do this nicer. That's probably not nicer, but I'm going to stick with that. Okay, so again, functional analysis and linear algebra equivalent. And the way that we should also interpret this is that these are now actually also solution coefficients, right? So this is also some sort of function in Rn. Okay, so our approach for solving this is that we're going to start. So we're going to look for an increment, delta phi, that fixes this problem, to fix this. To fix the problem of this not being equal to 0. Yeah? So really the exact phi that we're looking for would be r v phi naught plus some delta phi at our material point, such that this is now equal to 0 for all test functions v, right? That would be the true delta phi. Now clearly, that's not something we can immediately solve for, because, well, it's nonlinear with respect to that phi argument. That was the whole problem. But still, we can sort of improve this, right? If we have a nonlinear function, we're looking for its root, then what we do is we do a first order Taylor expansion. So we use now a first order Taylor expansion. What was that again? Well, that was simply taking the solution plus its partial derivatives or its directional derivatives in some direction that gives an approximation for that function in that direction. It's a forward order method, really. And we use this expansion to find an approximation, which we'll call del phi naught, an approximation to del phi. So we're going to use a first order Taylor expansion of the residual. What's that going to give us? We have the residual, which is still a linear form, but now at phi 0, plus the directional derivative of the residual in the direction of our phi increment. So that's a rather nasty statement. Let me just write it down a bit ambiguously for now, and we'll get into that for a second, what exactly that means. So I'm just going to write partial phi for now of r, which is a linear form, at phi 0 and at our parameter point, acting in the direction of delta phi 0, our approximation. And this is what we're going to set equal to 0. And that's going to be our first approximation of this del phi. Now, this is somewhat of an unclear statement. Let's take a look at this linear algebra equivalent to understand a little better what that is trying to tell us. In our linear algebra equivalent, we have the residual vector evaluated at phi hat 0 and mu, plus the partial derivative of our residual vector evaluated at phi 0 and mu with respect to phi, yeah, because our residual vector is dependent on phi, but phi hat in this case, and that's also a vector, and maybe I should also specify that here. So the phi's are vectors, right? So we set that here as well, phi's in Rn. Yeah. And this partial derivatives in the direction of del phi naught, so that is somehow acting on this vector del phi naught. Right? This is also again a vector, and this is a vector in Rn. And that's going to be equal to 0. So what objects am I dealing with here? Well, I'm dealing with an Rn vector, and the result is also an Rn vector. I don't know why I underlined that. And this increment, well, since phi is an Rn vector, also this increment is going to be an Rn vector. So what is this partial r with respect to the partial of the vector? Well, that apparently, if I look at these equations, that somehow has to be a matrix, right? So this is going to be Rn cross Rn. Because that multiplication with this little increment is going to give us a vector in Rn, so that I can have Rn plus Rn is a vector in Rn. Now we said linear forms are denoted as these Rn vectors. And we said bilinear forms have this matrix structure. So this guy is actually a bilinear form. Yeah, so the analogy here is that this is a bilinear form. And that kind of makes sense, right? Because, well, this was a linear form with respect to v, and it still is. But it's also linear with respect now to this function del phi naught. Yeah, this is a first variation. It's linear with respect to that. So clearly it takes it's linear with respect to two of these functions, making this a bilinear form. And since it's a directional derivative, right, the result has to be a scalar. This is an increment in a certain direction. So it's taking two functions linearly and producing a scalar that makes that a bilinear form. Okay, maybe this seems new, so let's try and connect this to the stuff that you're actually already familiar with. This is something that you're familiar with. This is namely the tangential stiffness matrix. And the bilinear form equivalent of that is actually the Jacobian. This is a bilinear form, which I'll call J, which takes as linear components v and del phi naught at the parameter point mu. Also evaluated at phi naught, and the parameter point mu. So this might also be a little bit confusing because we talked about Jacobians last lecture as well, and those were the Jacobians of mappings towards a reference configuration and back, right? We take the derivative of that mapping with respect to our coordinate. And a Jacobian in that sense is quite a general object that pops up in many cases. That is precisely what this is also. This is a derivative with respect to some object, a mapping or a linear form, with respect to all possible input states, namely in the direction of this del phi naught. Yeah? So there's a bit of overlap of nomenclature, but that's because deep down it's kind of the same thing but applied to a different framework. Okay, but still, the tangential stiffness matrix is hopefully something that you're familiar with in terms of nonlinear analysis. And also this increment idea, right? So we have a certain step, we take the tangential stiffness matrix, operate on an increment, and in our new step, so phi n plus 1 is then equal, where's the delta? Phi n plus 1 is going to be equal to phi n plus that increment that we find over there, right? So plus delta phi. And this is something that we're going to iterate through. And this is precisely the Newton-Raphson algorithm. Yeah, because if this increment was the exact increment that would satisfy this equation, then we will be done in one step. Well, clearly we're doing an approximation here with the first order Taylor expansion, so that we have a new approximation. We're going to do a new step, etc. So why am I saying all this? Well, I want to make you aware of the general structure of nonlinear equations. And the general structure that I'm talking about here is that in the end, what we are solving is still a bilinear form equaling a linear form. Bilinear form is equal to a linear form. And we're solving now for one of the components in that bilinear form, namely this increment, such that that is true for all our test functions. So note that in each step we are solving JV increment n, evaluated where the Jacobian is evaluated at phi n, and our material point or parameter point is equal to minus the residual, which was a linear function with respect to v, also evaluated at phi n and our parameter point mu. And this is really something that we're actually quite familiar with. Yeah, this is a bilinear form is equal to a linear form for all test functions. So this is for all v and h1. So even though we're talking about a completely different kind of animal, right? Nonlinear equations as opposed to linear equations, really all we're doing iteratively is solving a rather familiar linear equation. And the second thing that I would like you to note is that in that iterative step, we're kind of taking our previous solution as sort of a material constant, right? So this is somehow something that at that stage of our computation is taken to be a constant field. And that's going to impact our linearized equation. Yeah? So we can make a very strong analogy with material parameters here. And that's also what we're going to do in order to tackle this from a model reduction perspective. Now, let me also address that specifically. So, our previous solution, the previous solution, shows up as a material parameter or field. Okay, so let's make this a bit more specific and let's go back to our previous examples, right? Our material nonlinearity and our geometric nonlinearity. And we start with the material nonlinearity. So then our Jacobian, J, and I'll write N for material, which again is a bilinear form of V and some increment del phi. Sorry, I'll go back to the U, right? So now we're again talking about vector value functions. Evaluated at some displacement field U and some parameter point mu in our model reduction framework. What is this guy? So we've been saying this, or I just said that this is this funny partial derivative of the residual with respect to our field evaluated in a certain direction. This is a directional derivative. And our equation, I'll also kind of copy that one over. Our equation that we're dealing with was this one for material nonlinearity. So let me first write this down again so I don't have to scroll back up all the time. Yeah, so we're taking the partial of our solution field, partial U, of our bilinear form, which is this integral over omega of linear strain with respect to some strain-dependent stiffness, again acting on the linear strain of U. And not only that, it is also somehow acting in the direction of this increment del U. So let's make this more specific, right? So far I've been a little bit vague about a partial derivative acting in a certain direction, but this is actually something that you're quite familiar with. This is a directional derivative or a Gateau derivative. Yeah? So what we're doing is we're fluctuating our u a little bit in this direction, and then we're making the extent to which we fluctuate, shrinking that to 0, and we're evaluating that in a normalized sense, so dividing by that the length that we're moving forward in. That's precisely the Gateau derivative. And the way that we write down a Gateau derivative is that this is d epsilon of our expression where we're now replacing our solution u by u plus this epsilon parameter in this direction. So u plus epsilon del u. So sometimes they're already sort of referring to this del as a small increment. I feel that's a little vague, so I'm specifying the length of my increment with this epsilon specifically. Again, double contracted with the strain acting on u, but also with now this increment. And we're doing this as epsilon limits to 0, that's the way that we write that out, so this is evaluated at epsilon is equal to 0. Okay, now I can swap around the integration and differentiation, and then I can use the product rule to treat these separately, so I actually end up with two integrals. Of d epsilon acting on c evaluated at epsilon is equal to 0, double contracted with this one constant, plus the integral, right, product rule, with now the derivative acting on the strain. Okay, I hope I'm still consistent with all my underbars. So how do we deal with this? Well, this one is actually rather straightforward, right? Because epsilon is a linear operation. I could separate this out. And oh, sorry, again, this is also evaluated at epsilon is equal to 0. I could separate this into epsilon of u plus epsilon times, the strain of u plus epsilon times the strain of del u. Then I take the derivative with respect to epsilon, that kills the first term, and then I substitute epsilon as 0. Well, that's already removed due to this differentiation, so I only have the strain of del u. Now that's just all that the last term is going to give me. So this one is slightly more interesting. So we're going to have to do a chain rule now, right? So I have C being dependent on the strain, and the strain being dependent on this epsilon, taking derivative with respect to epsilon. So I'm going to have to do partial C, which is a fourth order tensor, partial epsilon, which is a second order tensor. So I'm not sure how familiar you are with your tensor calculus, but if you do the derivative, the partial derivative of an n order tensor with respect to an m order tensor, then the result is an n plus m order tensor. So this would actually be a sixth order tensor. So I need to double contract that now with, what did I write down? Well, with the derivative of epsilon, the derivative with respect to epsilon of the strain of this guy, and again that is linear, so that is simply going to give me the strain of del u. And this one has to be double contracted with epsilon of u. Now, does this make sense? I have here a second order, double contracting with something, double contracting with a second order. So that must mean that this is a fourth order, right? Just like the regular stiffness matrix or stiffness tensor is a fourth order tensor. Well, that was exactly, this is a sixth order tensor, double contracted with a second order tensor, gives me a fourth order tensor. So that makes sense. And plus, as we said, this guy actually is rather simple, the second term. Because that simply gives us the strain of del u. Because that was linear. Now I could say I'm done right now. I would like to rewrite this a little bit more though, to kind of clarify the point that I'm trying to make. I want to have everything in the form that kind of this one has. I want to have everything where I have really my standard way of writing my elasticity equations with some strain double contracted with the stiffness, double contracted with the strain. Which means that I have to shift some stuff around here. And I can actually do that because of all the symmetries in here. Yeah, strains are symmetric, well, it's a symmetric gradient of the displacement. Also my stiffness has all these symmetries in there. So what I can do is I can pull this guy actually up front here and do a double contraction on the left side with my stiffness. And that means that I'll get something that looks like this. So I now have this epsilon u double contracted with partial c, partial epsilon. And by the way, this is also evaluated that epsilon is equal to strain. And then I would still have this double contraction with epsilon on the right here. And that looks like this guy, so I can actually also already combine these two. So now I add this term in there, and I get C1, 2, 3, 4 of epsilon, the strain of u, double contracted now with this final terms. Okay, and this is a formulation that I'm happy with, and that is because this illustrates precisely the point that I'm trying to make here. And that is that this looks like the regular elasticity equations if we look at this guy as a new stiffness. And this is now a new stiffness that depends on the strain of our solution, right? And that's kind of making the point that I addressed here, that the previous solution shows up as sort of a material parameter or a field that affects the material parameter in a sense. And that's what we're seeing here. So in each iteration we in effect solve again linear elasticity, but with a funny looking stiffness tensor that depends on the solution from the previous step. And that also gives this notion of the tangent stiffness physical interpretation, because we're incrementing, and at each point the new stiffness is exactly what remains to be from the previous solution, the stiffness due to the previous solution. Okay. Yeah, okay, I think that's all I want to say for now. Let me actually conclude though. So again, this is the line that I started with. This is now equal to the Jacobian of our material nonlinear problem that is linear with respect to v, as you can see here. That is linear with respect to del u, right, as you can see here. That has, as a phi parameter, has a solution u in here. And also a parameter which might also be in here somehow. Okay. So this is how this fits in the framework. Now I'll talk about how to treat this from a model reduction perspective in just a second. First I want to discuss also how the geometric nonlinearities fits in the same view. So now we have a new Jacobian that we're interested in, JG for geometrical nonlinearity, which is again a linear form with respect to V, a linear form with respect to del U, so this is a bilinear form. Once it has been fed, once it has been given a solution U and a parameter point mu. Yeah, okay, now I actually think I'll do this in one step. Remember that the geometric nonlinearity, what did it look like? A bilinear form. Well, we took our standard linear elasticity equations and then we said we're going to do the strain differently. So we're going to keep the stiffness just perfectly linear. We still have the standard linearity with respect to the test function because that's what test functions do. But now we have this nonlinearity in our strain definition, which was the linear strain plus this correction. Yeah, so if I do my Gateau derivative, so my directional derivative, then I would have to vary this u here only. Wait, are you not seeing? Oh, okay, I think I've been thinking all these lectures that you can see my mouse when I point something out, because I can see my mouse. Okay. So this big E, that's the only place, yeah, that's where we're going to vary our solution U, which now has a linear dependence here, so that's simply going to act linearly, and we have to separate this out into as a product rule. Oh. So if I do that directional derivative, the Gateau derivative, then what I end up with is the strain of V double contracted with our constant stiffness tensor, double contracted with firstly just a linear strain of our increment, right? That was the linear part of the nonlinear strain, plus an integral where we're taking the gradient of our increment transposed multiplied with the gradient of our solution plus, and so this should be half here also half, plus the same thing but in reverse. I think it should be a single contraction. Okay. Now, so I actually looked at this for a while. I feel like you should definitely be able to rewrite this a little bit, but I didn't figure it out. But actually it doesn't really matter too much because it already illustrates all the points that I want to make. So where we saw before that sort of the solution from the previous state affects now a new effective stiffness field, what we see here is something that actually works a bit nicer, even though it doesn't look quite so nice, because what we see now is that this guy is a bilinear form. Let me do that better. This is a bilinear form. But these guys, they're linear with respect to V, they're linear with respect to del U, but they're also linear with respect to my solution. Yeah? So these are actually trilinear forms. And since I sum that, that's still also a trilinear form, so this is actually a trilinear form. And so I can actually write, So a trilinear, linear in our test function v, our increment u, del u, and our solution u. This means that I can actually write g as the sum, so v del u evaluated at u and our parameter mu. We can write this as the sum of some sort of bilinear part, which is dependent on v and del u and the material, plus a trilinear part that takes v, our increment del u, and also linearly u, still evaluated at some material point. So that works actually a little bit nicer than the material nonlinearity, right? This C can depend on del U in very arbitrary nonlinear fashions, right? We saw something that had just a kink in a material stiffness when we're talking about plasticity, but there could be hyperelasticity, right? There can be all kinds of funny behavior in our stress-strain curve. But for a geometrically nonlinear problem, we simply know that it's nothing more than the sum of a bilinear form and a trilinear form. So they're different is what I'm trying to say, and we also can see this from a model order perspective. So after about an hour, let's talk about model order reduction. So how about model order reduction? So because these two kind of show the nonlinearity in a different fashion, I'll actually talk about them separately, because we have different techniques for both. So our first step is really going to be the same thing. So we start as usual, we start or proceed as usual. Now what does that mean? We start by exploring our solution manifold in an offline phase where we have a whole bunch of computational expense that are available to us. We can look for many different solutions. We can compute many different truth solutions for high fidelity finite element simulations for all kinds of parameters mu, right? So during an offline phase, we explore the solution manifold and based on the manifold that we find, right, all the set of all possible solutions, we build a compressed space, a set of reduced bases, and we obtain our reduced bases, or reduced basis. So after we've done that, we have a set of basis functions that describe all the possible solution states of our nonlinear partial differential equation as effectively as possible. Now after that, we can write any model order reduced approximation of our solution, so utility, as the sum of, well, small n of our bases, right, times coefficients u tilde hat, coefficient I multiplied by some basis function psi. And this basis function would still be a function of space, right? And this is a vector valued function because we're dealing with vectors. So this is our reduced basis, some reduced basis. Which we could obtain from POD or from greedy, it doesn't matter. Now this is how we represent our solution. In the same sense, this is also how we would represent our increments in our nonlinear steps, or our iteration steps. So we have some sort of del u tilde. So we would also write that simply as the sum of a bunch of coefficients multiplied by our bases, which we found to be very effective. And now let me first discuss the geometric nonlinear linear partial differential equation. Now we start off with the bilinear form. That's still exactly the same as everything that we've done so far. So we're still going to assume that this guy has an affine decomposition, so it's affine decomposable, or simply affine with respect to the parameter point. So with respect to the parameter or parameters in mu. That's still a core assumption. Now secondly, what we'll assume that also this trilinear form satisfies this affine decomposability. And again, if it does not, then we would use like a discrete empirical interpolation method to force it to satisfy that. So we also assume, or I'm just going to state this, we're going to say that our trilinear form V del U mu, that is going to be equal to a finite sum of big Q T components, I think I'll be saying subscript T, from Q is equal to 1 of these phi's that depend on the parameter multiplied by now trilinear forms that are independent of the parameter. So this is our standard assumption of affinity. Now this is still a trilinear form, which means that for each iteration we have to substitute the previous solution in there in order to get a bilinear form. And hence the tangent stiffness matrix. Now what we can do, however, since we're only working with a relatively few number of these reduced bases, we can compute for each possible basis what the contribution would be. And that means that we can again, or quite literally, I'm simply substituting now this definition of our solution into our slot. Yeah? So in a reduced basis sense, if this guy is in a reduced space, this guy is in a reduced space, then that is going to be exactly the same as again the sum of your Q T components times now a sum of small n of the component, sorry, this is very strange. I can see the mouse, but I'm just changing it with the pen, but it doesn't show as changing on the recording software. So so the sum of now these coefficients u tilde I hat times, well, I can simply substitute that definition in the trilinear form, and it will give me that. Yeah, and I can do this because by definition the trilinear form is linear with respect to this u tilde, which means that I can simply substitute this sum and making this a linear decomposition. Now I can rewrite this a little bit to kind of make the point a little clearer that I'm trying to make. I can write this as a sum of a qt from q is equal to 1 multiplied by the sum from I is equal to 1 to n of phi's which are mu dependent, and these coefficients from our previous solution state times now new bilinear forms that are deduced from the trilinear form that are dependent on Q and I, that are dependent on V and del U. right? And I obtain these bilinear forms by substituting this constant reduced basis. This reduced basis is not going to change. This is a fixed basis for every iteration in our nonlinear computation. And I can keep that fixed, and then I can change this trilinear form into a bilinear form by simply fixing one of the components in the trilinearity. So these are going to be new effective thetas. Yeah? But other than that, this is again simply an affine decomposition, parameter dependent. Well, the solution from the previous state would show up in these effective thetas, but other than that, it satisfies all the affine decomposability that we require. We're able to compose or assemble our matrices effectively and efficiently during the online phase, and we're able to compute our solutions in each iteration very quickly. Now, it should also be noted, however, that clearly the number of terms that I'm going to need is going to be equal to qt multiplied by n. And suppose that our trilinear form initially had 5 components in the affine decomposition due to the parameter variability in our parametric partial differential equation. And suppose that we have 25 different bases in our reduced basis method. Which means that now q times 25, did I say 4 times 25, is 100 different components to a stiffness matrix. So clearly we have to store 100 stiffness matrices that are 25 by 25. Now that's still doable, but I hope you appreciate that at some point this scaling is going to be a little tricky. Suppose that we don't have 25, but we might have 100 bases, and this starts to become a bit of a bottleneck in the way that we approach this. But for anything that is of mild scale, this is still very effective. And so if you use many different reduced bases, well, actually that's also going to be a problem by itself, because each of the stiffness matrices for reduced basis is going to be a dense matrix, and you don't want to solve dense matrices anyway. So reduced basis methods in that sense also really depend on a small number of bases. Okay, so that is how we would treat a geometric nonlinearity. And maybe I should say this a little bit more general, not specifically geometric nonlinearity, but a polynomial nonlinearity, right? We see polynomial nonlinearity in the sense that, well, there's just 2 occurrences of phi and is linear, or of u, and is linear with respect to both. So another very classical case of a polynomial nonlinearity would be the nonlinear Navier-Stokes equations, right? So that would also fit in the same framework. Now, you could also design partial differential equations, or you could also be interested in partial differential equations that have a cubic nonlinearity, or a quadratic or a quartic nonlinearity. That would all fit in the same idea, although the number of sums would increase more and more. So I think that this is already starts to be a bit unfeasible for anything higher than quadratic nonlinearity. Yeah? But for quadratic, it's still what people tend to do. Okay, so that was the first case. So let's talk now about the material nonlinearity. Let me rehearse. We're interested in a bilinear form, the Jacobian, which is linear with respect to v, which is linear with respect to our increment del u, which takes as known knowledge our solution from our previous iteration and a parameter point. And our definition of this bilinear form was that it was the integral over omega of our strain field of our test function, double contracted with our stiffness tensor. But this was now this funny stiffness tensor that depended on the strain of the solution state, double contracted with the strain of our increment. So clearly this is the thing that we're somehow going to have to be able to tackle. And let's think about this a little bit, because this could be very nasty, right? This could be a very nasty nonlinearity. Could have all kinds of dependencies on our strain field of our previous solution state. And we've considered all kinds of options, right? We have hyperelasticity, plasticity, maybe there's a damage parameter in there, a hardening parameter in there. So we can have all kinds of functions in there. We could really have very nasty nonlinearities. But we're working with a reduced order space here, and that means that we have sort of already assumed or identified that the number of solution states that we are interested in is relatively finite. It's a thin solution manifold, right? In the sense of this Kolmogorov n width. And if there's really only a handful of relevant solution states that capture the complete solution quite well, then maybe there's also just a relatively small number of stiffness fields that are of interest to us. So, for any solution utility in our reduced basis, our new parameter, or new stiffness parameter C tilde epsilon of U tilde is just some solution or some function in space. Yeah, so let's take a look at some arbitrary examples. Suppose that we're dealing with a bracket that kind of looks like this. And we might have different deformation states that we're interested in, right? We might clamp it here, pull it here. And then we might have plastic behavior around these corners, right? So that would be a way that the stiffness would change. That C would change based on a deformation state relevant to this case. Yeah? Or, again, the same bracket. Or we might have a rolling support now, and suppose that we're pressing it on this side. Yeah? And we're also pinning it here. So you might get all kinds of plastic deformation again around this corner, but also on this edge due to bending, and maybe also here. So then we would have a material state that, well, around most of the bulk kind of looks the same as it did before, right? And even in this corner it kind of looks the same. It's just on this one corner that it looks different. Yeah, so in one more example, suppose that we're clamping it again on the left side. And we're pressing it up here, but we're also pressing it here. So there's really only bending around this corner, and there might also be a plastic deformation there. Yeah, so then we can already kind of start to get a feel for that, despite that we have maybe a relatively large range of real possible solution states, the states in which our stiffness field changes might actually be much smaller than that, right? There's only a couple of relevant ways in which our stiffness field changes with respect to our solution field. Yeah, so the point I'm trying to make is that if our solution space is compact, which is a core assumption in the whole model reduction process, then the space of relevant fields of stiffnesses, relevant C's, might be even more compact. Yeah, so we can again use some sort of model reduction technique to compress the potential states of our stiffness field. And this might work very effectively because, well, we're just interested in a handful of possible solution states anyway. Yeah, so this kind of hints at the use of, again, some sort of empirical interpolation method. So what we would do is we would try and write our effective tangent stiffness right now, C, which depends on the strain of some solution field, which is relatively finite, right? There's a thin solution state, a thin set of options, as a sum of QC now, if Q starts at 1, of again thetas, which are now somehow dependent on the state of epsilon multiplied by reference fields of C, which is again a function of space, right? Just like this one. So this is exactly what we talked about 2 lectures ago, that we were interested in trying to, with some parametric dependency, describe now a fluctuating field in space as just a handful of most important modes multiplied by these interpolation weights. And that's exactly what we would do here as well. So we would, in our offline phase, we would scan our complete range of possible solution states. We would, for each solution state, compute now a stiffness distribution state. We would also store that in some sense. We would do a model reduction on that to find the most important modes, the most important stiffness distributions that describe the whole range of possible stiffness distributions as accurately as possible. And then we would use some sort of interpolation algorithm, like either discrete exterior interpolation or just empirical interpolation, to come up with a affine decomposition like this. Yeah? And this is what you would then use in the nonlinear equations. So this is what you would substitute in place of this tangent stiffness, where at each new iteration you would get the coefficients corresponding to each of these components in a very localized way, right? So that's also one of the techniques that you would try to fit in here. You want it to be interpolatory, so that you have to evaluate these evaluations of these theta functions, which are a function of our strain field. You don't have to evaluate the complete strain field to get an effective theta. Probably what you want to do is you would get maybe a mode that only takes into account plastic deformation here, and then that mode would be connected to a strain state here. And similarly, you would get something around here, and maybe something also in this corner, or something like that. Yeah, but that completely relates. It's the same story as what we talked about for the lecture on discrete exterior interpolation. Okay, now that's pretty much all I wanted to say. Let me, however, also point out that in the context of nonlinear equations, the discrete exterior interpolation method is often referred to as a hyper-reduction method. So, in the context of nonlinear models, this is called hyperreduction. And there are more of these methods. So there are more hyperreduction methods. So this is just one of those approaches. Okay, now that's really all I wanted to talk about. So a bit of a summary at the end here. The nonlinear equations that we might be interested in could really range a whole spectrum of different classes. We've kind of looked at 2 separate classes because they fit so nicely for solid mechanics. That's this material nonlinearity and this geometric nonlinearity, where we saw that the geometric nonlinearity, in terms of how we solve that, is really just a set of iterative bilinear forms equal linear forms, where the bilinear form is actually composed of bilinear forms plus trilinear forms due to this the polynomial nature of the nonlinearity. And that fit very nicely in the reducible modeling framework because that automatically fits into an affine decomposition structure. Then for more like material nonlinearities, for every new solution state you would get a new material field, and that's also something that we've already looked at how to tackle that. That was with the discrete exterior interpolation method. Yeah, and that kind of summarizes what I wanted you to know about nonlinear problems. So thank you for your attention, and see you next week.